All right, now that I can take more accurate voltage readings and current readings from a circuit, I'm going to refocus back on building some simple logic gates, I think they're called, which is pretty much just logical operations using the physical components. So that's really the focus of this project and what I wanted to learn about. So to begin, I will list out the logical operations that I know about, and this is from a programming perspective. So maybe I don't know all of the operations that we have using the physical components, but I just know, I guess, the most common ones that I use at least. So first we have or, and we have not or, we have and we have not or not and then we have, let's say, exclusive or. So let me rewrite this one because it's not readable. And what are these doing? Well, we're pretty much just comparing two values and getting an output. So let's say we have value 1, which is called A, and value 2, which is B. Let's see how these operations apply. So in digital electronics, we have two possible values. We have a 1 or a 0. So I'm going to write it down here. I'm going to put 1 or 0. And this is also true. Or we could say a switch is on. Or we could say it's high. These all mean the same thing. 1, true, on, high. Or we have 0, which you could say is a false signal, or it's off, or it's low. And high and low are really used, I think, for circuitry, which the only reason I really know about them is because of simple machine buildings with microcontrollers and that kind of thing. So when you see 1, true, on, or high, these are all interchangeable, and these are all interchangeable. So how does this work? Well, if we have two inputs, let's say one is a 1 and the other one is 0. So that means that we have, let's say, two circuits, let's say a wire or LEDs. If one of them is on and the other one is 0, then if we were to use these as inputs in a logical evaluation with the OR operation, the question is, are one of these on, right? Is A or B on? In this case, A is on. So this would output a 1. Not OR is very simple. It's the inverse of OR. So we already did OR, so it's the opposite. So it's 0. There's only two possibilities in digital values. It's either on or off. And is also very simple. We're asking, is A and B on? Well, A is on, but B is not. So that's a 0. Not and is just as simple as not or. It's the opposite of and, so that's a 1, right? And then exclusive or is a combination of two of these, of or and and, or not and. The simple question, though, to ask yourself for XOR is, are they different? So if they're different, then we get a 1. Going with another example, let's say we flip these, right? Nothing should change here. Is A or B on? Yes, B is on. Not or, so is A or B on? Yes, so this is flipped to no. And is A, I don't know what's up with that beeping in the background. Is A and B on? No, they're not both on. And not and is the opposite. We're saying, hey, and is 0, so not becomes 1. Exclusive or, the same question, are these different? Yes, they are. So we got a 1 there. And technically, to build this out, we can't translate what I'm saying, hey, are they different, right, to a circuit. We need to really break it down by the logistics. So I'll do that. But it is a combination of or and not and. So we'll get to that. So let's make them both off, let's say. So they're both off. So is A or B on? No. So this is a 0. Not or flips to a 1. And are they both on? Definitely not. That's a 0. Not and. Right? Not this one. So it's a 0, so it flips to a 1. And exclusive or. Are they different? No, they're not different. So 0. And then if they're both on, right? Is one of them on? Yes. Not turns to 0. The AND gate is, are they both on in this case? Yes. Not AND flips to 0. And exclusive or, are they different? No, they're not different. So we get a 0. So that's pretty much the logic gates and how they work. So exclusive or, let's look more closely at exclusive or. Exclusive or is basically taking the outputs of two of these gates and then using an AND operation on their inputs. So if we have our OR result and our NAND result, right? And then we have a final AND. So for the first one, our OR and NAND are both 1s. So if we combine these with the AND evaluation, then we get a 1. If we, well, we know this is going to be the same. So let's say line 3, the OR result is 0, the NAND result is 1. So these combined with an AND, are both of these on? No. So we get a 0. So that's how XOR works. We're combining OR and NAND in an AND evaluation. The results, right? Hopefully that's clear. If not, when we build it, hopefully I can reach that point where I build it. I think it will become more simple. But XOR itself, we're just asking, are they different? So are these different? Yep. Are these different? Yes. Are these different? No. Are these different? No. And I think the others are really simple. So hopefully that makes sense. I should have also made clear on this real quick. We're gonna start this. That these are inputs, right? Input, and then this is output. Just in case anybody who's really new sees this. So these are the inputs. A is one input, B is another input, and then all of these are combining these and giving us a result. Again, just in case somebody is like brand new. All right, so now I will start with OR, I guess. There is technically one other thing that I should write here, and it's kind of assumed with these, and that is the inverse, the not. So not is the same as inversing. Inverse, right? So if we have a signal, let's say we just have one input, and this is say the not. If we have a 1, then not 1 is 0. And we have a 0, then not 0 is 1. And that's all that means. So on our first page where we are using not or and not and, you know, we're applying that same not operation to whatever their inverse is. So I guess when I make the OR gate, I should ideally be able to invert it by using a NOT gate or an inverter, which I would also need to find out how to make. So lots of fun challenges ahead, I think. So let's let's get started. We're gonna use transistors. I think there's probably a lot of ways to do an OR gate because I feel like if you connect you could connect so many things. I don't know what's conventional. I don't know what's the right way of doing it, but at least in my mind, there's a couple of different ways to do it. So first I'm gonna go back over the transistor, and this is a 3906 or something. I always forget. Is that focused? I cannot tell. Focus. Focus. Camera? Camera. Is that readable? I really can't tell. I can look with my eyeballs. 3904. So it's a 2N3904. Maybe if I put my finger here. Cool. Ah! So yeah. Don't look at my fingernail. It needs to be cut. 3904. 2N3904. And this is an NPN transistor, which means I have no clue. And when you hold it with the flat side facing you, then the pins are E, number 1, E, B, number 2, and C, number 3. EBC stands for emitter base collector. The collector takes a current, and the base, if it's powered, if it has a 1 signal or an on signal, a high signal going to it, it will allow the collector to escape out of the emitter. So the collector wants to leave out of the emitter, but he needs to ask Mr. Baseman if he can, and Mr. Baseman only says yes if he's getting a high signal. There's the 3-year-old explanation. So we need to use these for our logical evaluations. This is, I guess, what's done. These are what are used in processors and arithmetic units and all that. So let us get started. I'm just gonna stick this somewhere just to kind of get it moving. And all right, so we have, let me put my little dude back on. We have our collector, right? EBC, so collector's here. So we need to give this power so that it can leave out of the emitter. So I'm gonna move it forward a bit, and I'm gonna give it power from a resistor. So the collector has power. Okay. And now what I'm going to do is I'm going to add another transistor. I'm going to put him next to the other guy. So same thing. Flat side facing me for both of them, right? EBC, so we know collector. And then I'm going to tie the collector together for 2 of them. That means they're both receiving power. At least I hope so. So they're both receiving power from the resistor, right? So the power comes in through the resistor, goes up transistor A's collector, but it also continues down across the brown wire into transistor B's collector. So both of these should be collecting current together, and they're waiting for their base to be activated to allow the current to flow outwards. So what we need is something to show us the output. So I'm going to use our trusty red LED, and I'm just going to move it. I'm going to move it way down here, and I'm going to stick him straight into the ground and on line 23. So that's our output. So now we need, what do we need? We need our emitters to output to the LED. Maybe I should put the LED first. Maybe I should do that. So I'm going to put the LED over here. I think it will work both ways, but I'm just going to... Oh, wait, that will blow everything up. What am I thinking? Okay, so I'm going to put my resistor in. And then I'm going to tie it to my LED. Okay, I think this is better. Because this kind of shows, I think, more that the current's flowing and it gets stuck, right, until it has a way out. So maybe it illustrates it better. At least for myself, I think it's easier to kind of see. So we have our resistor going to the LED, which goes to both collectors, right? Because this collector gets it and this collector also gets it. And we're trying to find a way out. So I think we need to tie excuse me, the emitters together so that no matter who emits, it goes out. Or maybe I don't need to do that. All right, let me tie down the ground. Give ourselves somewhere for ground to access easily. Bloop. So this is ground. So right now we have our current going up resistor into LED into both of these guys. And we're just trying to find a way for them to get home. They both want to get home. They want to emit. So I'm going to add another little wire here. Let me tie this one over to connect them all. So right now, transistor B has a way for their emitter to go home. So we need A to also have the same path. So let me tie another cable down to the collector. Or I could just tie them together, I guess, the emitters, so that both of them can use this wire. So maybe that makes more sense. So I'm going to see if I have something long enough, or short enough, I should say. This one is not. This one's too long. Okay, here's another one. This brown guy. This guy. Yep, this one works. So what we have now is power comes in, goes in the LED, goes to both collectors, and A's emitter outputs from 14 to 17, where it joins this cable and goes out to ground. Transistor B takes power from the brown cable, right, coming from the LED. So power LED on 11 into the brown cable. Transistor B gets it in the collector, and then it can output onto row 17. So everything pretty much goes to row 17. Now, this should not work yet, right? Because, again, the transistors don't actually allow the collector to talk to the emitter until their base is energized. So these are switches, and the way that we press a switch, kind of like our old switch, right? We click and it turns on. Well, the way that we turn on the transistors are by powering up the bases, by giving it a high signal. So what we can do is get two more resistors. Damn, how am I going to fit little buttons in there? I don't know how. It's a little bit tight. I guess I could just use cables, which is the obvious answer. All right, so I need to just make some space. So we have two outputs. We need two buttons. So let's say button. Well, I guess I don't need to use buttons yet. I could just use resistors, right? Yeah, I'll just use resistors. I was hoping to use buttons, but... All right, so the base is going to get a signal from this resistor. So this one should be powered up. Or I should say the collector should be able to talk to the emitter. And then in this one, I'm going to also power up. If I can stick it in there. Oh man, he got all messed up. Okay, I think 13 is the base, and I'll put it in. Okay, so right now the bases are receiving power and the LEDs receiving power, and the LEDs power is going to the collectors, and then they should be going out the emitter. So this should illuminate now because both of them are turned on, both transistors. So let's plug in our power and hope that nothing explodes. Okay, so that's on. So by my logic, if we remove one of these, it should still stay on. But if we remove both, it should turn off, right? So this is an OR gate. We power it up, right? Right now B is on, I think. No, yeah, B is on, and now A is on. So this is an OR gate. It would be nice if these were controlled by actual buttons. So let me plug this out. Maybe I could do that. So let's say this is button B, and this, wait, I just put that in the wrong way. This is button B, and this is button A. All right, either the outputs are lined up into the base of B, into the base of A, and then I guess we need to power these. Oh, but this is not powered up yet. I need to share the power to this side of the power rail. Grr. And this guy gets power. Oop. And then I guess we just need to jump this over, which is kind of cool. So this guy, can you connect? Man, it's really tight, and that guy just flew away. He said no thank you. Alright, that's in. Man, super tight. I am not doing a good job at making use of my space. Alright, I think that works. And then this guy needs to also connect. He needs to jump over Mr. Brown guy there. I don't know if this is the right size, but I had it lying around. Maybe we get lucky. I think we are. Cool. So right now, both of these buttons are controlling these bases, right? Which will make it a little bit more responsive. But there's no power here. So let's do a little test. This should not work because the bases are not activated. Yeah, that doesn't work. Well, ooh, look at that. How does that work? I am so confused. Oh, you know what it is? It's when my finger is touching the resistor. Somehow, I don't know. I'm carrying some kind of voltage that activates the base itself. That's kind of cool. All right. But it doesn't work. Oh no, we lost one. Yeah, it doesn't really work. So what we need to do is transfer this power from this side of the power rail here. So I'm going to plug out my power, and I'm going to put this button back, a little slacker, and then we need to transfer the power. I do have some longer cables. That will work, I think. So positive to positive. It's not going to be pretty, but nothing is right now. That is terrible looking. I apologize. And negative to negative. These should be different colors. Man, this guy is long. But this works for now, right? I mean, I'm just trying to get a prototype. Okay, so positive to positive, negative to negative. I really should use different colors. I don't like how that looks. But I don't know if I have a different color that also reaches. Okay, my little My little orange guy is super long, way too long. And, oh, he's also gray. Yeah, I don't know. Red? Yellow? Ooh, how long is yellow? Oh, he's super long. Yeah, this guy is longer than my entire breadboard. Look at that. I could bend it. All right, I'll do that. I'll use this for the positive to keep it consistent, even though it really should be red, I think. But so we have this guy to the positive. Okay, this is somewhat good. So negative and positive. The yellow snake is positive. So now if we plug this in, we should see something happen. Hopefully no explosions. So now if we press a button, it should work. Boom. Nice bright red. Nice bright red. And this is an OR gate, right? A is on, B is off, but we still have a positive output. B is on, but A is off. We still have a positive output, and both of them give a positive output. So that's exactly what it should be for the OR gate. So that's the first one. Now I have no idea how we're going to flip this to a NAND gate. But this is a good start. At least it worked. And what I was saying before is I feel like we can connect even these outputs to create an OR gate. We could just use one transistor, right, and just connect the two buttons, and whenever one is on, the other one's on, and or we could just connect the bases, right? The bases could connect. We don't need this wire. We could just connect both bases. So I feel like there's a bunch of ways to make an OR gate. I don't know what's right, and maybe as I try to use this output, because I don't even know what I guess this is my output right now. Sort of. But yeah, anyway, this is a start. So that's cool. It's very interesting though how quickly it gets complicated looking. I know I'm not good at this at all, so it's more messy than it should be, but this is, it should be a very simple logic gate, and all of a sudden we have wires on top of wires, and so I need to get better at this, because if somebody told me to look at this, it'd probably take me a while to figure out what it is. Anyway, it works for now. Whee. Oh, he wants to come out again. A and B, A and B, and that does follow what we have here, right? Or A, B makes 1, A on, B off, A off, right? So A on, B off makes 1. The light is 1, it's lit up. B on, A off, the light is 1, or true, right? There's a high signal going through there, and that's why it's illuminated. Right now it's 0 and 0, both are off, and we have an off output, as we do here. And then 1 and 1, both of them are pressed. We get a 1 result, and oh no, we lost the other guy now. Let's see. I feel like we're placing Darth Vader's helmet on him. You shall be known as Darth. Button. Boom. So both are on when we activate both switches, or the light, the output's on. So that's a good start for me. I'm pretty happy that took one attempt. The buttons did give me a little bit of a challenge, just the spacing, but it's kind of cool to run it this way though. I like that. And this isn't my idea. I saw that on one of the pictures when we were looking at taking the voltage. Some people had it going down, so that's cool. Anyway, let's see what's next. I guess we need to invert